Good morning. Welcome to the second day of Real Pipeline Conference 2021 edition. It's a pleasure to be here. Today we start with a very special session. We'll cover integrity assessment technologies, okay? And this is such an important theme for the pipeline community. And this subject needs to be approached by different views. And that's why we have here in the room three gentlemen representing different areas. Okay, we have Pedro Risiuk from TGN, Argentina. Welcome, Pedro. We have Rafael Wagner from Sempis. Okay, welcome, Rafael. And we have Marcus Guinton from Rosen. Okay, welcome, Marcus. I am Mario Madureira. I am an Integrity and Maintenance Manager at NTS. I am very, very glad to be here today. I'd like to thank IBP's technical committee for inviting me, for playing this role as moderator. I'll do my best. The setup of our presentations today will be like, we'll have 15 minutes for each presenter, okay, to do their job. And then we'll have questions in the end of the presentation, okay? After all presentations are made, then we start the Q&A sessions, okay? So let's move on, we have a lot to talk. We'll start with Pedro. Pedro Risiuk is a mechanical engineer with a graduate certification in natural gas and a master's degree in business administration. He is currently the technical manager of TGN SA Argentina and responsible for integrity, with more than 20 years of experience in integrity management of natural gas transportation facilities. He is the president of the Integrity Commission of the IAPG, Oil and Gas Argentine Institute. Pedro's presentation will share the crack detection program that TGN is developing in their system, the tools that they are using, the results, the challenges, and they are facing, okay? Pedro, the floor is yours, please go ahead.
Thank you very much, Mario. First of all, thanks to IBP to inviting us, TGN, to share our experience in crack detection. So let's start with the presentation. Here. Okay. Sure. Is that okay? So excellent. So the idea of this quick presentation is to share with you the TGN experience in crack detection and management. So we will see an introduction of TGN network. Then our experience with longitudinal cracks, then circumferential cracks that we have in our system too. Finally, our crack management framework, and at the end, some challenges and final discussion that we are looking for the future. So when we see our system, it is a big system. It has almost 11,000 kilometers of transmission pipeline, gas, high pressure gas natural transmission pipeline. So it's a big net. Then we have 21 compressor stations. We transport 30% of the natural gas of Argentina. But our presentation will focus on the oldest pipeline that we have in our system. It was constructed in the 60s. It has a diameter of 24 inches, X52 the material, and the asphalt enamel coating applied over the ditch. When you see the picture, it is marked in the red line, in the thick red line, which goes from the north of Argentina to Buenos Aires. It has 1,750 hundreds of kilometers, and the MOP goes from 75 kilos to 60 kilos. The stress operation level is 72%, which is the design stress level that was made in 60. So it is a big effort to us to run this line in the safety way. And it is a line what was constructed with many manufacturers with pipes from different parts of the world. The different manufacturers are US Steel, Falk, Rainbow, Durham, A.O. Smith, Kaiser, CFI, and Mannesmann. But let's look at the A.O. Smith and the US Steel because this presentation will talk about it. So when we talk about longitudinal cracks, we have two threads in our system. First of all is the very known stress corrosion cracking in our system is the high pH SCC. But the other thread that we found not so many years before is the hydrogen embrittlement, more precise hydrogen environmental assisted cracking. And this is a new thread that we are working with. And the tools that we are using to detect these axial cracks are first the main tool is the image tool and the spike hydrostatic test, as the API 1176 says. The benefits of this contrast between the hydrostatic test and the image is that we can validate the image tool performance and to establish a safety factor and blunt the crack tips of this stress corrosion cracking or hydrogen embrittlement that we have in the pipe. Finally, the permanent mitigation that we use is the new coating, which we use the 100% solid liquids epoxy, like the permanent mitigation after the hydrostatic test or after a successful image run. Here we have some pictures about the threads. In the left, we have the pictures of the in-service rupture that we have in one part of our system. And there, the blocks that you see are a lot of colonies of cracks in this pipe. So we have a very interesting thread in this line. Then in the right part, you can see the hydrostatic test results where we have a rupture and we can compare with the image tool performance. The other threads that we found in our system is the circumferential cracks that are more related with the manufacturing process of the pipe. So here we are talking about the US Steel manufacturer line pipe that I talked earlier. So first of all, we use the hard spot detection tool that normally it uses for detect hard spot, like this name says, but we found circumferential cracks when we made the dig verifications. So we contrast this result with the MFL and we run to the pipeline material grade tool in order to identify these manufacturers that we talk about. But finally, when we found these cracks, we used the fractal mechanic analysis. So these are the tools, and these are some pictures of the threads. When you see the blue blocks are the reported by the hard spot tool, but you can see in pink the real crack, that it was a leak. So it is a contrast between the ILI and the reality. Again, you can see some other pictures with gas inside the line where you can see the leak, and some NDT test with the measure of the hardness, and then the magnetic particle test. In the left, you can see some the non-destructive test, and in the right, the hydrostatic test that where we found some circumferential cracks that not were reported. Finally, our crack management framework is, at first, we developed a crack management manual based on the API 1176. We work a lot about the IMAT performance tool framework. Here we hire a specialized consultant, and it was made with our historic IMAT runs, which are a lot of kilometers, 1,070 kilometers, 700 kilometers, and field verifications up to 150 digs, which is a lot of data to work with. The other thing that we finally arrived are the key performance indicators in order to accept or reject the IMAT run. And finally, the review and validation of fractal-mechanic calculations. In TGN, we used to make this fractal-mechanic calculations, so we hire an in-house fractal-mechanic specialist, and finally, we work a lot in training and certification. At the end of the presentation, we want to share some challenges that we are looking at, and that points are the IMAT tool validation process, that we want to increase the reliability because of the results between the hydrostatic test and the IMAT reports. Here we have to work very close to the ILI vendor. Then we will carry on with spike hydrostatic test. We will work with the continuous improvement of in-field verification test, NDT test, with more training and new technologies too. It will improve the management framework, and we want to work with the IMAT reinspection period between the two runs, and we want to go in depth about the pipeline materials data, and finally understanding and development of different crack growth models. This is our experience and the things that we want to share with you. So, muito obrigado.
Thanks, Pedro. Thanks a lot for your presentation. Excellent presentation. Me as also working as an operator, okay, like TGN, this SEC is a big challenge for us, okay, to ensure the integrity of our assets. We have some pipelines with this SEC thing, and it's really too good to hear from you, okay, your experience. Yesterday, I heard from Carlos Ranzani from TGN as well. His presentation showed how close we are in terms of actions to face the issues and to improve the integrity of our assets. By the way, if you and the audience allows me, I'd like to invite you guys to take a look at NTS virtual booth here in the pipeline, real pipeline platform, okay? There we took this opportunity to share many initiatives we're doing to improve the integrity program, about our assets expansion program, okay, about workforce training, cultural development, so many things. Please, I encourage you to spend some time on there, right? Now we'll move to Rafael's presentation. And Rafael Wagner dos Santos is graduated in 2002 in Materials Engineering from the Federal University of Rio Grande do Sul in Brazil. He started to work at the Petrobras Research and Development Center, CEMPES, in 2007. Since then, acting as a leader of projects for development of subsea inspection tools, pig inspection, structural health monitoring, and new NDT procedures and methodologies. Recently, one of his projects, the development of a multi-diameter ILI tool for inspection of subsea clad pipelines, was awarded in Rio Pipeline Conference 2019 edition, and also in CONAEND IEV edition 2021, okay? His presentation today is about low-cost inspection methodologies for pipeline integrity. Rafael, the floor is yours.
Thank you, Mario. I'm going to share my screen now. Let's see here. Okay, it's appearing for you? Yes. Okay, so let's move on. So first of all, I'd like to thank for the organizers as well for this invitation. It's an honor to be here, okay? And well, I'm talking about this idea that we have about how to use these low-cost inspection methodologies for pipeline integrity. Oh, let me use these arrows here. Okay. So the recent increase, let me just move the windows here. Okay. The recent increase in interest in low-cost pipeline inspection technologies and methodologies has been mainly due to the problem of illegal taps. Since 2016, it was a problem that we have detected here in Brazil. And this problem led to the need to increase the inspection frequency of each pipeline, which becomes very expensive when using traditional ILI tools. So the idea is use with more frequently, more often, these technologies to try to detect as soon as possible these illegal taps in our pipelines. So that's why we are looking for these low-cost inspection methodologies. So thus a program for testing and developing low-cost ILI tools was created internally at the company, okay? So it's about a 5 years program so far. Throughout the program, it was identified that there are major technologies and technologies with great potential for detecting illegal taps in pipelines. So an example, okay? We, alongside this program, we have contracted a pipe loop with different types and different sizes of taps in this pipe. And we have tried in this pipe different technologies in the market. And we have some partnership with Brazilian universities to develop this technology as well, okay? As an example of some of these technologies is in the left, bottom left. Let me point here the laser. And for instance, this is a section of this pipe loop where we have here 18 taps in a sequence. And you can see that one of these technologies could detect these taps. And you have blue and orange lines here. That's why you have more than one run. And you can see that for each one, they were able to detect these taps, okay? So this is a kind of technology, and this is a kind of how they show the technology. They show the signal. You know, it's like a scan. If you are used to ultrasonics, you have the amplitude and you have the time or distance here. This is the way they show the the signals. Another technology shows this kind of image here. So you have the A scan in the left, when you have the same section of the pipe loop for the other technology. You see here the drop in the signals, showing that the taps are detected, and you can see also like a kind of B scan, where you can see this loss of energy that's showing the taps here, the holes. So it's another technology that we have tested. It's a technology that we have developed with Brazilian university, and we are planning to license to the market near soon. Okay. And there are another technology that you can see like a C scan. You have the line scan, but you can see this line scan after in a C scan, that you can see the hole itself, like an image. So as I said here, you can see different kinds of technologies with different ways to see the data, but you see that all of them are able to detect taps. Okay. Okay, so you can use low-cost highlight technologies to detect illegal taps, but would it be possible to go further and use these technologies to detect other failure modes? And how about using low-cost methodologies to detect and measure corrosion, for example? Who knows? Huh? Why not? So let's try it. So what's the concept for this low-cost inspection for corrosion now? The concept lies in pipeline integrity management based on historical, operational, and/or inspection data, and on the use of simpler and more cost-effective highlight technologies, and how we think to use it. So there is an ongoing pilot project for subsea pipelines, and the choice to start the application of this methodology in subsea pipelines was due to the fact that the prominent failure mode of this pipeline is internal corrosion. And as this is the prominent failure modes, okay, we have more controlled parameters. So we have sensors that we can have the internal temperature, pressure. You have a periodic chemical analysis of the fluid. We have corrosion coupons that we can check how corrosive is the fluid. So you have many parameters, operational parameters, that you can have some information along the operational life. Okay, and for subsea pipelines, at least half of these pipelines are piggable. So we have also the pig data. So we can compare the operational data and inspection data, pig data, and then check a correlation between these, okay? And try to make a correlation of this information. So there's some examples of low-cost highlight tools. When I mean low-cost, because they are very simple. They have, just for clarify, this is not in scale, okay? This is a very small screen, very small sphere. In these are a kind of single module pigs, okay? Very simple pigs with some sensors. In the past, some may call this as ICIP, that's integrated cleaning and inspection pigs. So it's like a cleaning pig with sensors, okay? And these tools you can use, for instance, for comparison data. If you use every year, you can run these technologies and compare data to check if there are some difference between one year to another, or even to check the corrosion and measure the depth itself. Depends on the technology, depends on the tool that you are using, okay? Some of them have some this capability, the other don't. So, and about historical operational and inspection data. Let's think here. Suppose that we have the big data and have the operational data. If you have a cross relation between this data, you can check, for instance, this example, okay? If you have checked for many pipelines and you have seen this example, for instance, you have checked that for pipelines with more than 15 years under operation, if the corrosion coupon was more than 0.03 millimeters per year, they have the pig detected defects with more than 40% or 50%, for instance, of the depth or wall loss. And for instance, between 0.02 and 0.03, and more than 15 years, the pig detect between 30% and 40%, and so on. It's an example, okay? So we can put this in a matrix, put pipelines based on their nominal thickness and based on the potential production losses as a consequence of a failure, and use this as a base to select pipelines to use this low-cost special technologies. So you can see here, if you have a low historical coupon and corrosion rate, and we have a big, or at least a higher nominal thickness of this pipeline, the pipeline is in early operation. And okay, why cannot you use these low-cost technologies instead of these highly costly technologies? We can use this on these pipelines for a while, for 5 years, 10 years, 15 years, and get information for that, compare with what we have in the system, and you have this cost-effective savings in your integrity management, okay? And even in this situation here, if this line are not piggable, you can choose the technology to one of these lines to check the integrity of these lines here. So in this example, at least half of these pipelines could be inspected by low-cost technologies, and you can save money in your integrity management. So, but what are the next steps? Are we comfortable now with this low-cost technology? Not so far. So we are starting a qualification program using a pipe loop with controlled anomalies as a reference. This pipe loop, you have different types of anomalies with different associated wall losses. So we have general corrosion, pitting corrosion, axial groove, whatever, okay, with different associated wall losses. And we will establish detection capability and size accuracy of different low-cost technologies. And then after this, we will have a general overview of what's the capability and for POD and size and accuracy of this technology, okay? And also for some technologies that use magnetometers, for instance, this kind of program with notched defects, maybe it's not the best. So you use a subsea pipeline as a reference for this, okay? So this is, I would like to talk to you about this low cost, and hope to see you in 15 minutes for discussions. That's it, Mario.
Hey, Rafael, thanks a lot for your presentation. Very good presentation, and I'd like to congratulate you and the team for these efforts. Amazing job you guys have been doing. A lot of creativity, a lot of technical competence in there. Okay. Now we move to Marcus' presentation. Let me introduce Marcus to you. Marcus Guinton studied in Germany and China and graduated with degrees in civil engineering and business administration. In his professional life as an engineer, he worked on various construction projects for buildings as well as industrial and infrastructure facilities. Marcus joined the Rosen Group in Lingen, Germany in 2006 as a product manager. There he was in charge of the development and continuous improvement of various inspection and integrity services solutions. 2014, he was transferred to Rosen, USA, where he took the position of the area manager, West. In this role, he was responsible for the business development in that area. Today, Marcus is a global market strategist at Rosen, looking at future needs and solutions. Marcus' presentation will cover the advancements in MFL ILI data evaluation, and will share with us what is this evaluation heading to. Tell us, Marcus, what is that heading to? Go ahead.
Try my best. Thank you, Mario. Yeah, let me share my screen. Okay, you should see the right screen now, is that correct? Perfect, thank you, Mario. Yeah, first of all, thank you for having me, for the invitation. It's an honor to presenting today here. Yeah, as Mario said, the topic of this presentation is actually advancements in MFL ILI data evaluation. Where is it heading? And the motivation behind it is really, so the conventional MFL evaluation approximates anomaly shapes. So what operators are provided with are boxes in terms of length, width, and depth. And this leads typically to over-conservative results. We have an example for that, so I will illustrate that. And also the result correlation between repeat inspections is rather difficult. So we were asking ourselves the question, how can pipeline operators' integrity management programs better be supported? So to answer that question, we will first have a look at really high level, a little bit background on the MFL technology, axial and circumferential MFL. Then we speak to conventional data evaluation. What does it mean? What is being done as of today or until today? And then we speak about new technologies. One is AI-based data evaluation, and the other one is the so-called deep field analysis, before we come to the summary. Okay, the background on the MFL technology. So essentially you have two technologies, or at least it differs in magnetizing direction. So the more classic one is the axial MFL, that is called MFLA, or abbreviated in MFLA, where you magnetize the pipe wall in axial direction, also illustrated here. And the magnetic response, the leakage, is high if you have a circumferentially oriented anomaly, or an anomaly that has at least an extension in circumferential direction, a larger one like a round anomaly, for instance. An axial anomaly, though, due to the magnetic direction, the response is rather low. In contrast with the MFLC, the circumferential MFL, it's the opposite way around. You get a high response for like round anomalies. For axial anomalies, you get a strong response, but for circumferential anomalies, the response is rather low. And this needs to be considered in the methods, depending on what you want to achieve. Coming to speak to the conventional evaluation method. So what is depicted on the slide is actually on the left side, there is a corrosion anomaly with a rather axial oriented dimension. And here's the signal response from the axial MFL tool and the respective box that is created as stated in terms of length, width, and depth. And how it is reported with these parameters and an associated normal distribution in terms of accuracy, typically in depth, plus minus 10% wall at 80% certainty. And that is a population specification that in general, if you count all anomalies, is kind of valid, but there is differences between individual anomalies. So when you look at an individual anomaly, the signals do not necessarily exhibit a normally distributed error, but the signal is influenced, or the result is influenced by factors like tool speed, debris, anomaly shape, and so on and so forth. Now the effect of the boxing method. So what we see here is an example of repeat inspections with a 5 years time difference in between. It resembles, so the profile is very similar, as you can see, but there is some evidence of growth. Here the maximum is about 18%. We do have a constant R string, the effective area here. The real one did not change between the inspections. And just by transforming the signal response by the MFL technology, in this case an axial MFL tool, into boxes, this is the result in terms of boxes. What you can see is the shapes of the boxes have obviously been changed. There's a variation, but there's no clear corrosion growth evidence in terms of depth. And also what you can see is that the real area, the real R-string area, is smaller than what we are reporting, or what is being reported by boxes. And this is not a that is a conservative way of going about things, but certainly there's room for improvement. How can we get that? For one, there are AI-based methods, and we have been working on AI for quite a while. We do apply it, and this is a new method that we are working on, and that is transforming the MFL response, the signal response, so in terms of magnetic flux leakage, into anomaly shapes. And we are using a method that we at Rosen call direct inversion, meaning the transformation of MFL data response into profiles. And this is a predicted depth. It's not really calculated. It's knowledge-based. It's AI, artificial intelligence. And when we zoom into a couple of anomalies here, what we see, it's an approximation compared to validated laser scans. Still gives you a good picture of the anomaly, I think, but all the details that you can record with a laser is not recorded by this transformation. So what we can already conclude here is that profiles versus boxes, it's less conservative because you get a profile as opposed to just a box. And if you compare profiles between repeat inspections, that's much more comparable than just boxes. Another thing that it comes with the AI method is you want to explain it. It's going in the direction explainable AI to overcome the criticism of AI that it would be a black box. If you handle it correctly, it's not a black box actually. So we are generating, as stated, these profiles, and it's knowledge-based. It gives you multiple, I'm turning on this animation, it's giving you a multitude of possible profiles and also a multitude of possible boxes, and then a distribution with the most probable anomaly depth, length, and width. Depicted here is the wall thickness. And it's by giving you the most probable dimension, it is reducing the uncertainty. There's also another aspect of it, which is that MFL signals are not always, or there is some ambiguity in there. And sometimes what you get is a bimodal distribution, and that can happen. And this helps you to identify potential outliers. So last but not least, the deep field analysis method. As opposed to AI, it's not a prediction or estimation of the profile, but a direct calculation of the profile. And how it's working, what we have here is the axial MFL signal, and as recorded, and a calculation of the profile from that recording. And then what is being done is you can calculate back the signal from this profile. And if this matches, the calculated profile matches the recorded one, then you have a fit, then you're working with this. However, if in the first iteration, which it usually doesn't, it's a multitude of iterations, it does not fit, it goes back and optimizes it. So this is very calculation intensive, a very calculation intensive method. Now looking at MFLA and MFLC combination. So if we have a picture of that anomaly in terms of MFL signal in both directions, the profile gets much more accurate. It looks different to the MFLA alone, and this is also an axially oriented anomaly, as you can see. So there's no surprise that the MFLC has a better response or a high contribution to the accuracy of those results. And same story here. You calculate back from that predicted or calculated, not predicted, pardon, the calculated profile. You are calculating back the magnetic response, in this case, for both MFLA and MFLC. And there is again an iteration. As long as these two calculations, magnetic field calculations, do not fit the original one, you do not have the correct result. But if it matches, you have the correct result. Yeah, and this, what it shows you are on top of things, or on top of the screen, the upper pictures, the three upper pictures are calculated from both responses, MFLA or signals, MFLA and MFLC. So you get a calculated profile, and what you see at the bottom are laser scans, validated data. These were blind tests, and also what you can see here, the term that we use for it, it's a virtual digger. As you can see, the profiles are very accurate or resembling the laser scan very accurately. And when we look at the quantification here, we see like maximum depth, 33.4 compared to 37.9%. The calculated burst pressures, and that's maybe even the more important aspect of it, that you get a really accurate burst pressure calculation. Of course, depth is also an important value. And as you can see, it's in the area of maximum 4% difference. Here, it is even just 0.5%. So in summary, we have looked at these different methods. The conventional, which is absolutely knowledge-based. It's based on the experience of analysts, the training, plus the experience, the parameterization of the MFL signal, and from the evaluation, you get the box in terms of length, width, and depth. It is applicable to MFLA or MFLC. What it comes with is this population specification that we talked about, that you as an integrity or the integrity group later on applies on all the reported anomalies. It's obviously applicable to entire pipelines, and it is no surprise available today. It is a very conservative results. There is the overestimation aspect to it, and the result correlation is rather difficult. Now, coming to the AI method, it's also knowledge-based, but it's a machine that knows things. It is being trained on a lot of anomalies, validated anomalies. And it can be applied on MFLA and or MFLC. We have seen in this presentation examples from MFLA only, but in principle, you can apply it in both, either MFLA or MFLC or both. And what you get is profiles and boxes. The profiles, as explained, is a prediction. And what it comes with is an individual anomaly specification, which reduces uncertainty. And it is applicable for entire pipelines. It's actually rather quick, the calculation for an entire pipeline. It is, we apply it today already. However, we are continuously working on it. So it's partially implemented in work in progress. It reduces overestimation and contributes to the result correlation. So it improves it. Lastly, DFA, it's not a prediction, but a calculation. And it is, for us, it is mandatory that we have MFLA and the MFLC is required. So we would always do it on both due to the strength of both technologies that we have seen. And what you get are profiles. And these are calculated profiles. So you kind of overcome the need for experience and probability. And we call it a virtual digger. Where would we apply it? Because it's very calculation intensive and maybe it's not required for an entire pipeline, but rather locations of interest that are difficult to dig offshore. There could be various reasons for going this route. And what we say, it's applicable to individual joints or patches. Today, it is available for pipe body, and development beyond pipe body is in progress, so long seams, girth welds in these areas as well. The overestimation is essentially eliminated in this case, and the result correlation is further improved. So to answer that question that we posed in our motivation, so we think that the adoption of the new methods decreases, or we have seen that it decreases the overestimation and improves the correlation of repeat inspection results. And this really should help our operators to make better integrity management decisions, to really focus on the anomalies, the relevant anomalies, and to avoid unnecessary dig-ups. And lastly, I would like to thank my colleagues. Actually, I would say the brains behind both methods, AI and DFA, Christoph Hermes, Viktor Reimer, Niklas Wilming in the area of artificial intelligence, and in the deep field analysis field, it's Johannes Palmer, Andrei Danilov, and again, Viktor Reimer. And thank you guys for the contributions. Yeah, and Mario, I'm actually looking forward to the questions that we possibly have. Okay,
Marcos, thanks a lot. Excellent presentation. It's amazing how the artificial intelligence is helping, is provoking such a burst in the technologies that support the integrity assessment process. Mm-hmm. So I suggest to IBP to think of a new edition, to have specific sessions on how AI are supporting the integrity assessment process. So yeah, let's thanks again, Marcus. Great presentation. Let's move now to the Q&A session. We got many questions. I am sure we're not able to address all of them, but we start with Pedro. Pedro, two quick questions for you. What is the spike test pressure used? Is it more than 100% SMYS? What is the duration of the spike test? And also, during the recoating service, do you also inspect for cracks with PM, with magnetic particle?
Okay, so for the first one, the spike hydrostatic test is a test recommended by the NTSB, which is the National Transportation Safety Board of USA, and they recommend the hydrostatic test, which has to be made from 100 to 110% of SMYS. This is the range of the stresses that we have to put on the line in order to blunt the crack tip or to go to a rupture. So these are the stresses levels, and the time that they recommend is at least 30 minutes. So these are the questions for the hydrostatic tests, spike test. The second one is related with the recoating. So yes, we do the magnetic particle test when we make the recoating, because we dig the pipe and we make not only the magnetic particle, we use the phase array tool to measure the depth of the cracks.
Thanks, Pedro. Next one, we'll go to Rafael. Rafael, what is the main technology of this low-cost equipment? MFL?
So, Mario, actually, no, it's not MFL. Actually, I have the different kind of technologies in this low cost. And MFL is, for the technology that we have studied so far, MFL is not one of them, actually. because you do not need to, how can I say, magnetize the whole wall like MFL do, right? So we have technologies that use only magnetometers, for instance, in some of these technologies. So you don't have the magnets, only magnetometers, the sensors. Have technologies that use guide waves, circumferential guide waves, technologies at current. So they have different kind of sensors, different technologies. MFL, we can use MFL? Yes, maybe. With a single module, MFL, but maybe it'll be heavier than the other that you have so far. But it's a possibility. Yeah, it's a possibility. But you haven't tried this kind of tool so far, okay?
Okay, Rafael, thank you. And Marcus, how have the presented AI and DFA methods been trained and validated?
Yeah, that's a good question, Mario. What you need for the AI-based is really a lot of validated anomalies to train it. As stated, it's an experience-based system. And what we did, what you do is you get laser scans, AUT for internal anomalies, and you pick some or a fraction of that for training and the others for validation. So it's a vast number of anomalies. I won't say the number here, but it's a huge number of anomalies. With the DFA, it's a bit different because it's a direct calculation. You don't need that many anomalies to train and validate it. Yeah, but we also tested it, as you have seen, with the validation. With the blind test, we have also validated that on these anomalies, but as stated, it's not required to do that on as many anomalies as with the AI method. Mm-hmm.
Great, appreciate, thank you. And now going back to Pedro. Many thanks, Pedro. Regarding the MAT acceptance assessment, can you confirm when this assessment is completed? Is it upfront at the data quality gate or post-excavations when you have data supporting detection, identification, or sizing? API 1163 assessment. Thank you.
Okay, well, this is a good question. So the process is the same or follows the API 1173, which is the same for the MFL at first. We work with the tool specification first, then the tool reported defects, and finally the dig verifications from the tool reporting. So finally, we compare the field results with the IMAT reported defects. And finally, we make some calculations in order to have the KPI or the key performance indicators, which are related with good reporting defects, with false positives, false negatives, and no reported defect that we find on the pipeline. So finally, at that moment, we can decide if the tool the run is okay or not. This is a long process. I guess the question was answered.
Thanks, Pedro. Now moving back to Rafael. Is there any available data about probability of detection and sizing accuracy for these tools?
So, not yet. In terms of like POF requires 95% of confidence, this kind of thing. And for all type of anomalies. But we have some, that's why we are going to start a program for that. But we have some tests for some of these technologies that are very, very promising, yeah. And some of them you shows a good detection capability. Some of them a good sizing capability, accuracy, okay? But you have now to establish this data, okay? You have to establish this figure. So that's why we are moving forward to this and see, okay, these technologies, how can we use really, and for what kind of defects? Well, for this pipeline, what kind of corrosion we expect? What kind of defect we expect? Then we can choose this technology to low cost to use in a routine for this management, integrity management.
Good, thanks, Rafael. Marcus, which tool to select for the right kind of tool selection when you don't know the defects in the pipeline?
Yeah, that's a good one. So ideally, of course, you have an idea, and I would start with a threat assessment to identify what do you expect. If you do have little information, then it becomes difficult, and maybe it's advisable to do both. But with a threat assessment, I would say you can identify the more suitable technology. The more classic one, of course, that you also use in baseline inspections is the MFLA technology, the axial MFL. So maybe that's a choice to start with if you have no idea where to go. But also I want to refer to my colleague, Roland Palmer-Jones, who has a talk about predictive analytics, which is quite interesting. So there you can take information that you have, put it into a model, and it will give you at least some indication about the condition of the pipeline. I recommend for you to look at that, which could contribute to your risk assessment, actually.
Thanks, Marcus. Okay, it's Frenetke here. Okay, now to Pedro. Sorry. Oh, my bad here. Yeah. Pedro, have you found HIC cracks in pipes from a specific manufacturer or from more than one? Are these HIC related only to manufacturing processes, or are other contributing factors present?
Okay, good question. Well, we have found this threat, the hydrogen embrittlement, related with these two manufacturers, mainly A.O. Smith pipe and US Steel 2. These are the manufacturers that we're working with in order to hydrogen embrittlement. And the other factor that contributes to this threat is the levels of cathodic protection, that these levels were high. So with the time, working with the specific material, maybe it can grow. So these are the two main components for the hydrogen embrittlement development.
Thanks. Guys, we have just 2 minutes left. Let's make it very quickly for Rafael. In your presentation, Rafael, you said the next steps include field trials. In these trials, are you planning to inspect pipelines where you have recently used conventional ILIs tools?
Oh yeah. As said in the presentation, for instance, when you use technologies that only magnetometers, for instance, if you use a pipe loop with machined defects, you can really have some stress on this around these defects, so it can make easier the detection of these defects for this kind of technology. So it's not so proper. So we are using these subsea real pipelines with known defects. So if expected by MFL pigs, expected by UT pigs, the same pipeline, and you run this technology on this pipeline to check the detection capability, compare with this pigs inspection as well, and the sizing. So yes, we will compare with the pipeline that you have run, other technologies.
Okay, folks, under protest, I have to close the session. I was told by the organization that our time is over. From the amount of questions that the audience has made, I think we have satisfied the objective of this session. So thanks a lot, everyone, for your support. Thanks, Marcos, Rafael, and Pedro, for your effort and your collaboration to make this session very successful. Thanks a lot. Enjoy the rest of Pipeline Conference.
Thank you, everybody. God bless you all. Bye-bye.